Sorry for the late start here. Are there any questions?
When we're using the neutralization of ammonia, when you reach the neutralization point, why don't you have to factor in
Sorry.
hydronium produced by ammonia at pH?
Why don't you?
Yeah.
So, if you're titrating, let's say, ammonia with a strong acid like HCl, so we'll have milliliters of HCl here. You're going to start off on the basic end of things.
Yeah.
And then eventually you'll hit the equivalence point. At the equivalence point, the reactions is ammonia plus HCl. This is going to yield ammonium chloride. Okay. And so the thing is, we do factor in the hydronium produced by the ammonia, because if we didn't, the pH should be 7, right? But it's not 7. Actually, the pH is going to be less than 7 at the equivalence point. And the reason is because we're factoring in the ammonium. We have ammonium chloride, which is the salt. And so we're going to have Ka from ammonium, and then Kw, which would contribute to the hydronium. This is just an acidic salt. And so we would factor it in. Okay, but we probably wouldn't factor in Kw because it's so minor.
But Ka for ammonium is also pretty much 5.55 to the negative 10.
Yeah, it's 5.55 times 10 to the negative 10, but it's still not 0. And so it leads to, the pH is going to be kind of low. The pH is going to be like 4, 3. pH is fairly acidic. When you do the pH calculation. Okay. Other questions? This is what we call a base titrated with an acid. It's just a curve flipped upside down because now we're starting at higher pHs, like lower. If we started with sodium hydroxide and titrated with HCl, then the equivalence point would be at 7. There the only hydronium ion producer would be water, since sodium ions are neutral and chloride ions are neutral. Okay, other questions?
How do you tell a pH indicator, like phenolphthalein will be colorless or not? I know phenolphthalein, but just let's say a generic.
You look it up
Okay.
in the book, see what color it is. It tells you the acid color and the base color, but acid color is deceptive because acid doesn't mean pH less than 7. Acid means that the pH is less than the pKa. And the base color is the pH is greater than the pKa. And so the base color of some indicators actually comes in at very acidic pHs, like pH 4 is the base color, whereas pH 2 would be the acid color. And so it's just relative to the pKa. And there you just find it in the book. There's a chart, a nice chart in our book that shows the colors of the indicators. Some of those indicators are polyprotic acids, so they have multiple colors, not just 2. Okay, any other questions? All right, so we did the fractional precipitation, is that correct? Yeah. So what are we going to do next? Fractional precipitation is an example of controlling solubility by using the common ion effect. And so that's one way we can control solubility, common ion. QSP and KSP. Another way we can control solubility is by using pH. Let's look at solubility in pH. There's some, as these carboxylic acids, these organic acids grow pretty big, they become less and less soluble because the organic part of it becomes more dominant than the polar part. And so if we look at one of these large organic acids, let's say solid acids like this, what's the KSP equation or something like this? So we start off with a solid. We're going to go to H plus and A minus. It's just, assuming, just dissociates like that. And so pH is going to have an impact here, right? If we look at the pH, increasing pH means more soluble or less soluble? Increasing pH means the solubility increases. Decreasing pH means the solubility decreases. This is a common ion type problem. The pH is going to tell us the H plus concentration. From that we can figure out how that. If we look at things like magnesium hydroxide on the basic end of things, this is going to go to magnesium 2 plus 2 hydroxides. Here, it's pretty easy to figure out, pH, how that's going to impact this. Increasing pH will decrease or increase solubility? Decrease solubility. Decreasing pHs increase solubility. Qualitatively, we can see that. If we want to do this quantitatively, we just plug this into an ice table. We did it before. Quantitative. We call it the common ion type problem. Right. And so this is common ion. That is, you can see that the pH is going to have a direct impact on one of the ions. There's something that has a less direct impact, and sometimes it's hard to see. So let's take a look at that. And that is something called KSPA. This is SP, regular, and this is A stands for acid. And so it's acid's impact on the KSP equation. KSPA. So let me give you an example of KSPA. KSPA occurs when we have basic anions that aren't hydroxide. There are lots of basic anions that aren't hydroxide. You look on the chart over there, see a lot of anions there, which are capable of accepting a proton. And so something like this, calcium carbonate. Calcium carbonate solid goes to calcium ions and carbonate ions. Calcium carbonate is limestone or calcite or marble. Not marble, marble's mixed, but it's not very soluble. How does pH impact this? pH is not going to have a direct influence on any specific hydroxide or hydronium in this because we don't see any. But carbonate, calcium ions are fairly neutral. Calcium, the cations of the strong bases, what are the cations of the strong bases, cations of the soluble hydroxides? Group 1, calcium, strontium, those are neutral. Those don't really hydrolyze water. The anions of the strong acids, like nitrate, iodide, neutral, chloride. But carbonate is basic. This is basic. If that's a basic ion, then if I make this solution more basic or more acidic, I could get more to dissolve.
More acidic.
Yeah, if I make it more acidic. And so what happens is as the pH goes down, it becomes increasingly acidic. As it becomes increasingly acidic, well, we're going to consume base. And so if we consume base, then the solubility should go up. Whereas if we make the pH more basic, then the solubility actually goes down. This is qualitative. But how do we do this quantitatively? Well, quantitatively, this turns into a multiple equilibria problem. We have calcium carbonate like this, right, solid. We're going to go to calcium 2 plus carbonate. We can consider multiple equilibria like this. The other equilibrium is carbonate. Carbonate is a base, so carbonate is going to have what kind of equation? What's carbonate going to do once it gets in water? Yeah, it's going to collide with the water molecule and accept a proton. Actually, carbonate is what we call a dibasic base, right? So it's going to go to bicarbonate and hydroxide. So this is KB1 for bicarbonate. And then we have a KB2 as well. I'm not going to write the KB2. So how do we handle this? Multiple equilibria situation like this. We have the KSP and the KB1, the KB2, and the KW. So, if I want to figure out what's going on in this equilibrium, especially how pH impacts that, the pH is going to be the total equilibrium hydronium concentration, right? But, this is a base solution. There should be a basic solution. And so we don't look for hydronium ion contributors in a base solution. We look only for hydroxide ion contributors. So we got to figure out all the total hydroxide here. That's going to give us our pOH. And then we can see how the pH impacts the pOH, which impacts the equilibrium here, the multiple equilibria here. And so when you're faced with all these equilibria, how should we do it? Should we do the KSP first? And then the KB1? And then maybe KB2, maybe KW? Depends. How do you want to deal with this? And so we got this multiple equilibria like this. And so what's the approach? We should use?
We have to start with KSP to find out how much carbonate is all you purchase.
Right. And then some of that carbonate should hydrolyze water. Why don't you try this? Give it a shot. I'll give you a few minutes to see, at least figure out where you're going to start. If I wanted, okay, let me give you an actual problem. How about that? You want an actual problem? Let me tell you this. This is the actual problem here. What's the solubility? At pH, should we go? You want to go high pH or low pH? Let's go low pH. Not that. Let's say, what's the solubility at pH 4 point? There's our water. Would our water eat up limestone? What's our water? 4.5? Yeah. Let's see at 4.5. What's the solubility of this at the pH 4.5? Our acid water. What's your overall assessment of this problem? Pretty straightforward? No? Pretty easy? No? Pretty tough? Or doable, manageable?
Doable, but we're not there yet.
Just need a little bit more time. Well, you see, this problem can be solved pretty quickly, actually, much quicker with a different technique. We haven't talked about it yet. The approach for this particular problem is going to be the combined method. Yeah, I just continuously reporting. So let's use the combined method for this. What the combined method is we don't deal with this here. This can get difficult, right? Would you say difficult? Because you know what you have to do. What's the method you have to use for this? Simultaneous. It's a lot of equilibria. 1, 2, 3, 4. Simultaneously. This is too much. But maybe it's necessary. Maybe there's no other choice, right? But there could be another choice as long as you have a very special scenario. If you have this very special scenario, you could use the combined method. Okay? And so what is the very special scenario? The very special scenario is this. We take the calcium carbonate solid. And so we start off with our regular KSP. But in the next one, look for everything that can be attacked by acid, H3O plus. And so, what can be attacked by acid, H3O plus, up here? Well, if I think about what is the base, what is the strongest base present here? The carbonate. And so I'd say carbonate would be attacked by H3O plus to form what? HCO3 minus N, water. Now, if we have a strong acid like carbonate reacting with a weak base, strong acid like H3O plus reacting with a weak base, then we say that K is very large, very, very large. But in this case, we aren't going to say K is very, very large. In the combined method, what we're going to do is we're actually going to figure out what the K value for this is. And so what is the K value for this particular equation? Can you see? Well, the K value for this, look at this reaction going backwards. What is the reaction going backwards here? Ka for bicarbonate. So this is 1 over the Ka for bicarbonate. Now, we look at just what hydronium, what acid will attack in the original equation here. I don't look at, acid's going to attack this too, right? Well, we're going to ignore that. We're just going to look, what does acid, well, it's just going to attack the carbonate. And then what we do is we combine these two equations. And so we combine them. And we get calcium carbonate solid plus H3O plus is going to produce Ca2 plus HCO3 minus plus H2O liquid. The K for this final equation here is just KSP over Ka for bicarbonate. This is what we call KSPA. KSPA. The problem with doing this is something disappeared. What disappeared out of the equilibria? Carbonate. Does that mean carbonate doesn't exist at equilibrium? No, carbonate exists at equilibrium, right? And so that's an error there because, according to mass balance, when we're looking at the solubility, all the carbonate in this will be converted into bicarbonate. Now, I said that the combined method only works for a specific scenario, and this is the specific scenario it works for, or is reasonable for. Number one, this has to be very small. For this method to work, the first one has to be very small, which tells us very little carbonate is produced. The second one has to be very big, saying that any carbonate produced is attacked by hydronium, formed bicarbonate. And so what do you think? Is calcium carbonate very soluble in water? No. And so that meets the first criteria. Very little calcium carbonate should dissolve. And the second criteria is this K going to be very big? Yeah, I mean, strong acid, right? Weak base. We'll have the number here. It might not look so huge, but this is what we're going to consider big. Does it make sense? And therefore, the amount of free carbonate should be negligible. Therefore, free, what we call free carbonate, this is not free because this is bicarbonate. The free carbonate would just be CO3 2 minus AQ is negligible. And so what this does is it just makes your life a lot simpler. ICE. Right? That's all we have to do. And so we could solve this problem quickly if we want. Let's finish it now. So I have the calcium carbonate solid plus H3O plus going to calcium 2 plus bicarbonate plus H2O liquid. KSPA for this one will be equal to KSP of calcium carbonate over the Ka for bicarbonate. Now, the thing is, is the pH 4.5 initial or final?
Initial.
It should be initial because if I'm just using our water here, or DI water, or whatever, was our DI water that acidic? No, it was 699. It was tap water, huh? What was tap water? 5.5? Did anybody measure that?
Yeah.
So 5 something. All right. Well, let's say this is not our water. Let's say we have pH 4.5. This is acid rain. That's pHs of this or lower. that would be initial pH, right? Because that would be what's attacking the limestone. And so if that's our initial, in this case, I'd say initial. But not in every case. Sometimes it's final. You have to read the question carefully to see. Sometimes the solution's buffered. If the solution's buffered, what does that tell you? We can assume that the pH doesn't change. And so whatever the hydronium is initial, the buffer compensates, so the hydronium will be the same initial and final, or close enough. And so if this is pH 4.5 initial, then that means the initial hydronium ion concentration is 10 to the minus 4.5 molar, which is equal to what? .16 times
10 to the negative 5.
times 10 to the negative 5. All right, 3.1. Actually, we're only allowed 1 2 here because of pH, but I'll carry extras. 3.16 times 10 to the negative 5 molar. What's our initial calcium concentration? 0, because we assume nothing's dissolved yet. And bicarb? 0. This is going to be minus x molar plus x molar. Oh, is it x or s? Let me ask you that. Okay. X or s? S. It should be s. Minus s plus s plus s. So we get 3.16 minus s molar, s molar, s molar, where s is the molar solubility.
What's the difference?
S is the amount of calcium carbonate you'll be able to dissolve. It dissolves. S goes this way usually, unless there's some initial calcium.
Can you just call it X?
You could call it X. You know. Then you'd have to later on figure out what X is. Is X the solubility or not? Because usually I'll ask for the solubility. Okay, what's easier? Simultaneous, multiple simultaneous, or combined? Combine's pretty easy, isn't it? But does combined work for everything? No, but lots of people try to make it work for everything. You know, once people know the combined, they go, "Oh, that's the easiest way." You know, for example, phosphoric acid. Phosphoric acid, H3PO4 plus H2O liquid, yields H3O plus H2PO4 minus. Step 1. H2PO4 minus is H2O liquid, yields H3O plus HPO4 2 minus. HPO4 2 minus plus H2O liquid yields H3O plus PO4 3 minus. And they go, oh, this is so simple. I just combine all three. So H3O PO4 plus 3 water yields 3 hydroniums plus phosphate. And then the K for this is Ka1 times Ka2 times Ka3. Good? Would you ever do that? No? Why not?
Because non-negligible concentration of H2PO4 minus.
Yeah. But if you recall this calculation, the amount of free phosphate was negligible. I mean, it was tiny. You know, the bulk of this was from Ka1. And so the major species would have been H3PO4 and H2PO4 minus, and then it just decreases as we go down. And so doing combined would give us a big error because we're assuming all the phosphorus ends up in phosphate, and there's no dihydrogen phosphate or monohydrogen phosphate. Does that make sense? And so is this good? No, this is not good. We can't use the combined here. What is the scenario where we can use the combined? Yeah, first step is very small. Second step is very large. Then it works. Or, close enough that we can ignore. It's there, really we should do this multiple equilibria to get the minute, but this will give us a reasonable answer without too much work. So that's an example of a combined, and then we have a special case, sulfides. Sulfides are going to be different. Sulfides are highly insoluble, so let's say we had something like lead 2 sulfide solid. When we look at the KSP is extremely small. But there's something interesting about sulfide. What's the difference between something like sulfide, which is dibasic, and something like carbonate, which is dibasic? What's the difference between sulfide and carbonate? Both are dibasic, so that's similar in that way. But sulfide is a strong base, and carbonate is what? Not
strong.
Yeah.
Sulfide,
Yeah.
almost doesn't use.
Sulfide is a strong base. Are strong bases like sulfide stable in water? No. So this turns out not to be the KSP equation. The problem with this is that sulfide is too strong. All right, and sulfide is going to hydrolyze water. And star on base is going to hydrolyze 100%. This is a one-way reaction. What is this going to produce? HS minus and hydroxide. Now we combine these two equations and we get PBS solid plus H2O liquid goes to PB2 plus HS minus plus OH minus. We don't calculate it. This is going to be KSP double dagger. KSP double dagger is for sulfides. The KSP equation does not look like your normal KSP equation. That's because sulfide's immediately going to attack water. And so for the KSP equation for sulfide looking like this, we get that it's going to equal the PB2 plus concentration times the HS minus concentration times the OH minus concentration. Okay. So sulfides are different. The KSP is more complex. Now, how does pH impact this? Well, it looks like the pH just impacts it directly, common ion. Because pH is going to change the hydroxide. Increasing hydroxide pushes it left, Decreasing hydroxide pushes it right. And so it looks like it impacts the hydroxide, but HS minus is amphoteric. HS minus is also a base, or can be. You know, it can be an acid too, but it's a base also. And so should we just ignore HS minus? You know, because if HS minus is a base, what's going to happen with pH? Will it impact? You know, HS minus is going to have a Ka and a Kb, which is going to get impacted by pH. If you look back at the other common ion ones, we didn't have this complication. Like magnesium hydroxide, you got magnesium, which is neutral, and hydroxide. And so there it's a very simple common ion. But this is a complex one because the problem is it does look like just a simple common ion type problem, but HS minus makes it not so. And so how do you deal with this? Well, I guess I could do KSP, then I could do Ka for HS minus, Kb for HS minus. And did you know hydroxide is amphoteric too? Suppose I could do Kb for hydroxide, but we already know nothing's going to happen. And Ka for hydroxide. Should I? Should I worry? Well, all of a sudden things get all mixed up, right? Especially if you're confused. And you have all these equations that you can add to it, but the simplest thing is to forget all that simultaneous equilibria and then see if what method might work. Combined method. And so let's do the combined method here. And so let's see, pH and solubility. When I'm thinking about pH, I'm thinking about acid, you know, H3O plus acid. How's that going to impact this? And so this will be the KSPA double dagger. So let's check out the KSPA double dagger, which is going to be PBS solid plus H2O liquid. Is going to go to PB2 plus HS minus plus OH minus. What's acid going to attack first in this equilibrium mixture? Hydroxide. And so the acid will attack hydroxide. Hydronium will attack the hydroxide, which is going to produce H2O liquid, 2 of these. And so we need KSP double dagger. We have that. We need the K value for this because if we're going to do the combined method, we actually need the numerical values here. This one, you know, what was K for this one? Just very, very large, or no, actually, sorry, very large. KB is very large. And so this is going to happen. So KSP already incorporates that. We don't have to do anything because it's already happened, right? So somebody tell me what the K value for that equation number 2 is. It looks like it's going to be very, very, very large because it's a strong acid with a strong base. So it's got to be very, 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 very large, but we need a number. We have to have a number for this. Yeah. What is it? 1 over KW. Right. 1 over KW. Now you're going, you know, if I could get the number, why don't I just do the ice? Why don't I just do the ice for everything? Why do I make this very large, very, very large, and very, very, very large? You know? And to be honest, when we do the very large, very, very large, and very, very, very large, do you know what we're doing? When we make that assumption, like your book does, you know what they do? When they assume the very, 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 or very, very, very large, they're saying the reaction goes to completion, right? But then, do you know, you do another step. And when you do another step down here, you let it equilibrate, and you end up with some of the species that you lost earlier. And so essentially what you're doing is you're just resetting the equilibrium. And so when we say very large, it resets it this way, right? And then you do another calculation, and the calculation that you do subsequently equilibrates everything and fixes that assumption. Does that make sense? In other words, well, we'll just continue here. Yeah, we don't have to worry. We just go, it's very, very large, so it's a one-way reaction, or very, very, very large, it's a one-way reaction. Goes to completion. Later on, we might fix it. It depends on what it is. It's for just electrolyte, salt, probably not. All right, the problem with this is we would just stop here, and that would look like a normal KSPA type problem, but we don't just stop here because HS minus is also a base. And so once I've attacked the hydroxide, hydronium in the original equilibrium can attack HS minus, which makes H2S and water. What's K for this? We'd say very, very large, strong acid plus weak base. But we need a number, so the number is going to be 1 over Ka for H2S. Do you see that? If we reverse this reaction, it's just Ka, acid plus water. And so combining these three equations, we get PbS solid plus H2O liquid is going to go to Pb2 plus. Oops, I screwed it up. Sorry. Didn't add it right. Sorry. It's going to be PbS solid plus 2 hydronium goes to Pb2 plus H2S plus 2H2O. This will be KSPA double dagger, which is going to be KSP double dagger divided by KW and KA. So here, if we're given a pH, we've got to figure out, is that the initial or the final? Sometimes it's the final, like for example, when a buffer solution. And then we just fill out the rest of the ice table and see what the solubility is. Because that's in the next step. When we're looking at KSPA, we always just look at what acid attacks in our original equilibrium. The bicarbonate was a product attack. And so, yes, you could go with the subsequent step there, but that would be like a secondary effect, not the primary. The primary is what's going to be attacked in our original equation here. And to be proper, you should do that, see what happens with bicarbonate, but we are, for our KSPAs, we're just looking at the original. Okay, any questions on the KSPA? here. Okay, the final method we'll talk about is actually KSPS. F stands for formation. And so formation of what? Formation of a complex. And so the first thing we'll look at are KFs. KF is formation of 1 mole complex. 1 mole of complex from the free metal ion and free ligands. And so let's take a look at some KF equations right now. Copper 2 ions, free, plus free 4 ammonias, 4 NH3s, will yield the tetramine copper 2 complex. I'm going to omit the square brackets just because it gets confusing if you have square brackets upon square brackets. One square bracket indicates the coordination sphere. The other square bracket indicates the concentration. So let's omit the one for the coordination sphere and just look at the concentration one. This is called the KF for copper, the tetramine copper 2 ion. The KFs are typically very large, very favorable. KSPs are typically small. So let's try a problem here with a KF. Okay, what is the solubility actually, I'm jumping ahead. What is the, sorry, let me cancel this one. What is the free copper 2 concentration in a solution that is 3.0 molar in free ammonia? So what do I mean by free ammonia versus what? Free ammonia versus what? Yeah, this is what we call, the ammonia on the left is what we call free ammonia. The ammonia on the right we call complexed ammonia. The total ammonia in the solution is equal to the free ammonia plus the complex ammonia. That gives us a total ammonia. And so, let me just write that here. Total ammonia equals free ammonia plus complex ammonia. So, this calculation here. Let me set it up. So if I have copper 2 plus 4 ammonia, I'm going to yield the complex here. I need to fill this out. So what do I do? Do I have enough information to solve this? Where does 3.0 go?
Under the 4 inch.
Is it the initial, right here? Or is it the equilibrium, final?
Initial.
It's the initial? You see, sometimes it's ambiguous. Sometimes it's hard to tell. Well, in this particular problem, you should be able to tell, what is the free copper 2 concentration in a solution that is 3.0 molar in free ammonia? So it's got to be final. Do you see that? Yeah. It's got to be 3.0 molar final. So let's figure that out. Am I missing information? Uh-huh.
How would that be stated if it, for it to be in the initial?
Oh, how would it be stated if it were initial?
Yeah.
I'll try to make it clear. Like in a solution initially that is 3 molar free ammonia. And so I'll try to make it less ambiguous. In the homework, it's sometimes it's a little bit confusing. So you can't tell, so you assume one. Usually if I ask people to assume one, they always assume the easiest way to solve it, whereas I wanted a little bit more challenging problems. If it's really ambiguous, assume, but try to figure it out. Okay, now what? Do I have enough information to solve this problem? Do I know what the initial copper 2 or the initial ammonia is? In other words, do these have to be a 1-to-1? Looks like they're 1-to-1, doesn't it? It's 1-to-1 mole ratio. Are they the same? Is the copper 2 concentration equal to the Are they equal? Yeah. No, because, yeah, you're right. It depends on KF. And KF for this is quite big. How big is it? If somebody has their book. 1.1 times 10 to the 13, which tells me that it's mostly going to be this. The 1-to-1 just means if I lose most of it, it's going to be converted to this. And that's all. It doesn't mean they're the same concentration. It's mostly this. Well, do we have enough information to solve this? We don't have enough information to solve it to a unique answer, but we can solve this to a general answer. That is, the KF has to equal the copper mean 2+ concentration, tetramine, and the ammonia concentration to the 4th divided by the copper 2+ concentration.
Why is
Why?
ammonia on top?
Oh, it should be on the bottom there. Actually, it's right. So we don't solve this to a unique answer. Some people will say, we aren't given enough information, and we'll just stop there. But on open-ended tests, that aren't necessarily asking you for a specific answer, just it's open-ended. You don't want to stop. You want to just keep going. And so if we were to keep going, we'd see that the complex over free constant ratio will have to equal 1.1 times 10 to the 13th times 3 to the 4th, which is what?
8.91 from 6 to 14.
Times 10 to the 14. So this pretty much tells you that the ratio that you have to have is 10 to the 14th would be what? 10 to the 6th, 10 to the 9th billion, 10 to the
100 trillion. 890 trillion.
something like that. 890 trillion. Is that? It'd be, yeah, 890 trillion to 1, which means you have a lot of complex. In fact, the free ion concentration is going to be very small. And so if you're given a problem where it looks like you're missing some information, we can either solve it to an equation, like a ratio like this. This becomes more and more, more and more common as you progress in science, because, when people ask questions, do they give you a lot of specific details, like, oh, yeah, tell me what happens when the copper 2 is 1.36 times 10 to the minus 6 molar, the temperature is 28.3 degrees C, and so on and so on. Do they give you a list of specific variables that they want the answer to? No. When somebody usually asks a question, it's kind of open-ended. They don't have a specific number. They just want you to tell them what kind of happens, right? And so rather than coming up with a number, okay, if they gave you 0.100 molar here, yeah, sure, we could guess the number. We have 0.100 molar here, then this got to be this concentration, right? But, as you progress, people want a more, this is what's going to happen kind of thing. They don't want one specific tree in the forest. They want the whole forest, and they want you to give you a broad overview of the whole forest, right? And so for those types of things, you look at these types of scenarios where you have some kind of equation like this, or you think in terms of extremes. If this were 0.1, this would be this. If this were 1, this would be this. If this were 10, this would be that. That kind of thing. Does that make sense? And so, yeah, this is ratios, huge. Which, you'd expect, because this is a huge number. Right? All products, very little reactants. 3 molar. Yeah. And so we could solve problems like this, where we look at, if this were 3 molar, what is our total ammonia you know, what would I have had to start with? Let's say I started with 0 here, and I had some amount here. What would this also be 3 here? What would the total ammonia must have been at the start of this? If, let's say I just had free copper and then I added ammonia to this, what must have been my initial ammonia concentration here?
Three molar plus initial copper 2 plus. Because it reacts as almost all.
Okay. Yeah, 3 molar plus initial copper 2 plus?
Yeah.
No, the hydrogen complex.
Mm,
4 times.
would it be 3 molar plus 4, which is 7 molar? No. It would be whatever this concentration is times 4. And so if this were 0.1 molar, then this is pretty much close to 0.1 molar. So it would be about 0.4 molar, just a hair under 0.4 molar. And so I would have started with 3.4. Because, you know, it pretty much, if you look at a ratio like this, it pretty much goes close to completion. Not exactly. And so these are the types of things we think about when we're doing these, you know, free, complex concentrations, and that kind of stuff. And sometimes it can get confusing. Well, let's do another problem. We're going to do a KSPF problem now. So that was a KF problem. Let's do a KSPF problem. What is the solubility of copper 2 hydroxide solid in 3.0 molar ammonia? Let's try that here. So we're dealing with solubility, so we want the KSP equation. Copper 2 hydroxide solid going to copper 2 plus plus 2 hydroxide. This is KSP. In 3.0 molar ammonia, now we know that ammonia attacks copper 2, right? And so we look at this equation. Will ammonia attack hydroxide? No. And so copper 2 gets attacked by 4 ammonias to form the complex here. This is KF. And so if we combine these two equations, we get KSPF. Is it okay to combine here? What are we missing in the combine? What are we missing? The free copper ion. And so we're going to say that the free copper ion is negligible, so we could ignore it completely. Is that an okay assumption to make? Yeah, I mean, because KSP, number one, KSP is kind of small. Copper 2 hydroxide is insoluble. And number 2, KF is huge. The ammonia scavenges out the copper 2. And so this is a very effective way of dissolving it. Now, we come up with our ice table here on the combined, and we've got to figure it out. Is this 3 molar initial or equilibrium? Yeah, in this case, this 3 molar has to be initial. Do you see the wording difference there? And so this is initial. What's my initial copper complex? 0. And hydroxide? 0. And so the change is going to be minus, no, not minus S. Minus 4S. Minus 4S plus S plus 2S. And so we're going to get 3.0 minus 4S molar, S molar, and 2S molar. And so we just plug in, K for this is going to be KSP times KF. You look at the values in the book. And this is just going to equal the complex concentration times the hydroxide ion concentration squared divided by the ammonia concentration to the 4. That looks easy to solve. I mean, look at the 4 second. Solve it for S. Right? Does this look like an easy problem to solve? No. In fact, what would you do when you're faced with a problem like this?
You do the simplified assumption to get a baseline and then use successive approximation.
Okay. Is the simplifying assumption likely to work in this case? It's unlikely to work. It turns out that this, even though this is very small and this is very big, K comes out kind of big. This is why it's so easy to dissolve copper 2 hydroxide and ammonia. And so unfortunately the simplifying assumption doesn't work, so you could just go straight out to successive approximations. Or you could do it and then assume it's going to be way off. Or, one way, why do I say the simplifying assumption is not going to work? This K is kind of big. So what would you do in that scenario? I wouldn't have gone this far. I would have reset this right away. Reset, because I know if this is kind of big, I should have reset it. And then I would have used the simplifying assumption. I might not even have to use successive approximations. I would have reset this. And what would it reset to? Let's see how good you are with your numbers here. Well, the ammonia is going to go to what?
0.
0. Three fourths here? Yeah, that looks right. 0.75 molar? And this would be 1.5? Okay. Now the change is going to be plus 4s, 4x, minus x, minus 2x. Is X the solubility? No. So we have to go back and figure out what the solubility is. All right, so we'll just try to solve this right now. Does somebody have the KSP value for copper 2 hydroxide handy?
How do we go from S to X?
S is the maximum amount that's dissolving, but we dissolved more than the max. We're more than the max. Now we're going to go backwards, fix it. And so we'll relate S to X in this problem. We'll finish this problem. Let's go ahead and finish this in a couple of minutes. Does somebody have the KSP value handy?
2.2 times
2.2 times 10 to the negative 20. Wow, that's really small. 1.1 times 10 to the 13. Oh, maybe this doesn't look so promising. Maybe I shouldn't have reset it. Let's see. We'll just try and see if the simplifying assumption works or doesn't work. All right, so if we go on here, and then we get the K for this one, the KSPF is equal to what? (2.2) times 10 to the minus 2.42 times 10 to the minus 7. 10 to the minus 7 seems like you're right. We probably shouldn't have reset it. But since we already reset it, let's just go ahead and try it, see what happens. And so that's going to be 0.75 minus x, 0.75 minus x, times 1.5 minus 2x, divided by 4x to the 4th. Hopefully the simplifying assumption works. So we'll try the simplifying assumption. This is going to give us 0.75 times 1.5 squared divided by 4x to the 4th. That means x is equal to what?
Got
8,883. Did the simplifying assumption work? No. Failed. It failed. It failed because I was guessing KSPF was going to be big, but it turned out to be small. And so if it's small, then it tells us it's mostly reactant. And so I need to reverse what I just did and go back to this one. And then try it.
Using what? Excessive?
No, we'll try the simplifying assumption. And so let's revert back. Oops, we're out of time though. We'll revert back to the original and then try it, and then see what happens.